I'm not gonna have boxes.
There's no such thing.
But
I tried.
They should be right.
Oh yeah, no. Certain family size. Whatever. Yeah, like that. It's like when you say, I don't know, just ready,
Okay, I'll do it.
Were you vlogging? Yeah, exactly.
So, we're getting comfortable with matrices and matrix properties. I wanted to mention something just to start, and I wanted to fill in something that I think we didn't do, but I'll ask you when we get there. But first, let me just say this. A lot of stuff that we're doing and writing down and showing up in slides with matrices kind of looks really familiar. It almost looks like the same thing you learned ages ago when you learned about scalar multiplication and scalar addition and scalar, all these properties that of multiplication and addition. So most of it is the same. It is in fact a generalization of what you learned with scalars. And it's a generalization because, maybe this is obvious, but I want to make sure everybody realizes it. A vector of length 1 is a scalar, and a 1 by 1 matrix is a scalar. So if the rules that we give you for matrices don't generalize properly, then something must be wrong, because those count as matrices and vectors. A scalar is a matrix, it's also a vector. It's a kind of silly one, right? It has only one element, but it still is a matrix, it still is a vector, either one. And so all the rules that we give you have to work if you reduce them to that case. That's why they look so familiar. But there are some things when you generalize that are different, and that's what I just want to warn you about, to make sure that you don't get too comfortable looking at it and saying, well, yeah, it's just like the scalars. So let's just check through a bunch of things that we know about. In the scalar case, actually I wrote them in the order I didn't intend to. Let's do associative first. What's the associative rule for scalars? Let's write like the scalar case, right? You do something like this. 2 scalars multiplied times a third scalar. You can group them, right? Those things are the same. You can multiply the A and the B first, and then multiply by the C, or you can multiply the B and the C first, and then multiply by the A, and it doesn't matter, right? That's the associative rule. Same thing for matrices. If these were matrices, same rule. Exactly the same, nothing changes. Matrix, product of matrices corresponds to a cascade of linear systems. In this case, it would be 3 of them. The C comes first, because that's the thing that's going to act on the input. And a product of 3 matrices, you can use the associative rule just like you do in the scalar, right? What about distributive? So that's associative. Sorry, I was a little bit off in terms of alignment. What about distributive rule? Remember that? That one looks like this. Right? This is about mixing multiplication and addition. So A times the sum of B plus C is AB plus AC. Again, if these were vectors or matrices, that would also be correct. They have to be appropriate for multiplication, right? The usual rule that the height of the width of the matrix has to be the same as the height of the thing you're multiplying it by, right? So that's not correct, then that doesn't make sense. But if alignments are correct in terms of sizes, input and output sizes, then this works for matrices also, just like it's written, no change. Distributive, okay? So these two, the matrix case, is just identical. Exactly, I'm just going to put a check mark. It's exactly the same if these things were matrices as if they were scalars, okay? What about commutability? So that says that A times B equals B times A. So you know that that can't in general be true for matrices, right? Because the rule for multiplying two matrices together, the rule about them being suitable for multiplication is that the width of the first one has to be the height of the second one, right? But the other two dimensions can be anything. So automatically you see that AB, it might not even make sense to do BA if the dimensions were not matched up, right? It says so this is not necessarily true. It's certainly not true for all pairs of matrices A and B, the way it is for all scalars, right? Any two scalars, this is true. But it's not true for all matrices. There are some matrices for which this will be true. And the closest thing we have to this, the thing that kind of looks like this, but it's not the same, goes like this. Actually, so this is my chance to make sure that we did this last time. Mike talked about transposes, right? Okay, so I'll do the other thing in a moment. So transpose, here's a visual mnemonic for a transpose. Here's a matrix. Those are the columns of the matrix, right? First column, second column, third column, etc. I always, I don't know, maybe this is me, because I think in geometry, and especially 3D geometry, I imagine this diagonal like this. And then I imagine rotating this piece of paper in 3D around that diagonal. So if you notice, here, let's mark them in color. That one, I'm going to mark in blue on both sides. And this last one, I'll mark in red on both sides. A little prop. And then I will trash the rest of them. Okay. So there's columns. And the first one is blue and the last one is red. It looks like somebody's flag. I'm not sure whose. There's a diagonal. I'm just going to flip it like this. And oh, what happened? The blue one, which was the first column, is now the first row. And the red one, which was the last column, is now the last row. So all the rows and columns, rows become columns, columns become rows, but you can kind of visualize it like that. Okay? All right. So, what else can we say here? I want to write if I have a product of two matrices, A, B, I'm going to make them capitals for matrices. These are because they're small, right? And I'm thinking about multiplying these two matrices. One way I can think about this is I'm taking dot products of the rows of this guy with the columns of this guy. And so I'm intentionally writing this one in terms of columns and this one in terms of rows. Right? We can think about a matrix in terms of its rows or in terms of its columns. It's the same box of numbers. It's just about how you are compartmentalizing it so that you can make use of it or think about what's going on. Okay, so I'm just choosing. I'm making a choice, an intentional choice, to select the rows here and to select the columns here. And why am I doing that? Because I'm kind of thinking about what's going to come out of this product. Each element that comes out of this matrix product is going to be a dot product of one of these row vectors with one of these column vectors. And in fact, what will show up in the output is every possible pair of dot products. Every row of this with every column of this. And if I want to know what is the ijth entry in the output, the answer is I take the ith row of this and the jth column of this, and that dot product of those two vectors is what gives me that entry in the output matrix. Okay? So I'm going to take all possible pairings and products. Okay? Now, if I want to transpose this entire thing, every element in that output, A times B, is the product of the ith row and the jth column here, I now want the thing that was the ijth entry to become the jith entry when I transpose it. So now I have to take the jth row, I have to take the jth column of this and the ith, switch the indices, right? I have to take the jth row here and the ith column here and take their dot product to put them into the output. Or I could say, well, what if I swap them? This is A and this is B. What if I rewrite them? I want to write something that looks like B times A, right? We're trying to get to the issue of the commutative rule. So in scalars, it just looks like that. AB is BA. What happens in matrices? I want to somehow switch the A and B, but I can't really do that. But what I can do is notice that if I do B times A, that's not going to work because that's going to be taking dot products of the what? The rows of B with the columns of A. So I'm going to get not the same numbers that I have here. Here it's the rows of A and the columns of B. I want the other way around. So how can I flip it around so that I'm not multiplying the rows of B, but the columns of B? Sorry, not the columns, yeah. This is bad. I want that, since B is first, I need its rows. That's how matrix multiplication works. But I don't want the rows, I wanted the columns. So how do I switch them? I have to switch the rows and the columns. So maybe if I transpose it, I transpose this one. So now B is on the left, but it's transposed. So it looks like this. I should have written them in colors. Sorry. This is now B transpose. And these rows of B transpose are just the columns of the original B. Right?
So there's 5.
I transposed it, right?
So there's 5 rows.
True. I drew too many. But who's counting? Actually, you're counting. I know that. We've answered that question. What question is left? A. What about A? Well, over here is going to go A transpose. A transpose. And then now, instead of the rows, which are marked in A, those are now going to be the columns of A transpose. Ah. And there were 1, 2, 3, 4, 5 of those. And I've got 5 of those. Okay. So now, the matrix multiplication is the rows of B transpose times the columns of A transpose. But those are the same vectors that we were multiplying here, dot products, right? These were the rows of A, which are the same as the columns of A transpose, and the columns of B, which are the same as the rows of B transpose. So it's actually the same dot products that are showing up here that were showing up here. I flipped the order, but I also transposed them so that I'm flipping rows and columns, okay? And then the last thing, of course, is that this thing is going to give me back a product of all the rows of this and all the columns of that, but they're going to be not in the same places that they were here, because the ijth element here was the ith row of A and the jth column of B, and the ijth element that's going to come out of this it's the other way around. It's the ith column of B with the jth row, or sorry, ith row of B transpose, or column of B, with the jth column of A transpose, or row of A. Okay? So they're going to be backwards, and that's okay, because I can just take the thing at the end and transpose it. So, let me write that down up here. A times B is not equal to B times A. But if you do this little tricky thing, where you take B transpose, and you take A transpose, and then you transpose it at the end, then it is correct. And of course, that now specializes to the scalar case. If these guys were scalars, what's the transpose of a one-by-one matrix? Well, it only has one entry, and it is both B column and B row. So you would transpose it, it just sits right where it is. So a scalar, the transpose of a scalar is the scalar. So this is the scalar case. This is the same as this. But the generalization requires you to put in the transposes, because you can't do this with matrices. Okay? And then we have a slightly special rule for the commutative law. It doesn't behave the way it does in the scalar case. It's a little bit more extensive than what you have to write out. Let me just also point out, when you transpose a matrix, and you already saw this because I flipped it back and forth, but I'll say it explicitly. Here's my matrix, and now I transpose it. If I transpose it again, what happens? It goes back to the way it was. I can keep doing this all day, right? I need my diagonal. Everybody sees, right? If I flip it again, flip it again. This is a flag waving in the breeze. Somebody's flag with blue and red on the two sides. Okay? So when it keeps flipping, it's a weird way to wave a flag in the breeze. It's got a pole that goes up diagonally. So it's been mismounted. Now it's doing this, and you have to turn your head 45 degrees, and then you see what I was saying. Everything works. I knew I did get that to work. Okay, so the point is, very simply, that if I transpose something twice, it goes back to the way it was. Transpose and then transpose again is just an identity operation. It does nothing. Okay? So of course, if I have an equation, I can transpose both sides. So I can take this transpose out here, and I can move it over to the other side, and maybe the equation gets a little bit nicer. It says that if I want to transpose the product of matrices A and B, this is important, this is going to show up a whole bunch of times, I have to transpose each of the individual elements. So think of this as like a special distributive law for transposition, right? So here, distributive law for multiplication, A getting distributed over addition gets applied to each of these elements, and then you add them together. What if I have a transpose and I want to distribute it over a product? That's what we're doing here. Here's a transpose, and I'm trying to apply it to this product AB. What I have to do is apply the transpose to each of the individual elements, A transpose, B transpose. But now we notice that A transpose, B transpose might not be suitable for multiplication because I just flip the columns in the rows, so they may not even match. And in order to make it correct, I have to transpose A and B and change the order, which is exactly what you see, right? So if I want to transpose a product, what I do is transpose the individual elements and reverse the order. Just reverse them. B transpose A instead of A transpose B. Okay? So that's a little tricky, but it actually is just kind of mechanical, right? It's just about which columns and which rows, and it's really hard. If you can write it all out with indices and notation, and that doesn't make it any easier to understand, unless you really like reading notation and you get into having everything precisely written out. I don't find that helps. For me, describing transposes this way is more useful. And I hope that you at least got the sense of what's going on here, why we have to flip it like this. Okay? All right. So that's commutative. Commutative is circled in red because it's a little bit different for the matrix case. Right? You can't just do the usual thing. You got to remember transposition. Yes?
You want to do the trivial even rotation matrices don't commute? No, up to you. I think I meant to do the diff.
Let's leave that. Because I'm not saying that a nice way to say.
Oh, I just pick up an object and click it.
Yeah, well, for those of you that have taken physics, you might know that. That's one of those things you learn in physics when you're trying to describe 3D coordinate systems and talking about spinning tops and things. But otherwise, it's a little bit hard to get your head around. No. I'm going to leave it.
I'll do it during the break.
You do it next time. You do it during the break. We'll have a halftime show. I have music, and so you're going to get music that you don't want. Okay. The additive identity. What can I add to a scalar that doesn't change it? Zero. And what's the additive identity for a matrix? A matrix filled with zeros, right? It's kind of obvious. It's just because, why? Because addition of two matrices just means add up all the individual elements. So it follows directly from the scalar case. You're just adding up scalars anyway. So the identity for addition is the zero matrix. You add the zero matrix and nothing happens. So this is just, A plus 0 equals A. And again, I'll put a check over here because the matrix is no different. It's just exactly the same thing. I'm kind of liking getting these off the floor. It gives me, a morning of deep knee bends or something. And I know it won't fall any further. That's as far as it goes. actually, I shouldn't say that. The way this building is constructed, I'm sure there are holes in the floor underneath these tiles. So this could go. Anyway. All right, so that's the additive identity. What about the multiplicative identity? So what do I multiply a by to leave it alone? If it's a scalar, 1, right? 1, I'll write it this way, 1 dot a equals a. Everybody knows that. What about the matrix version? Well, it's I, right? So it's a matrix it's a diagonal matrix containing all ones, a square diagonal matrix containing all ones, and we usually write it as I. Sometimes people write ID, or if you're writing MATLAB, you would write EYE, haha. So this is the identity matrix of the correct dimension. So it has to be the right dimension as usual. But otherwise, I times a vector or a matrix, we'll write it as a matrix, because a matrix is a vector, or it can be a vector. So I'm just writing this for matrices. This could just as easily be a vector. Okay? And the last one is an inverse. So a multiplicative inverse I should have written.
Oh.
So I
spaced that, but works for square matrices. Can work for others if you want to go up to full. I mean, in math, 1 times a is a times 1. In matrices, that only works if the shapes are right.
Yeah, that's already covered though in the commutative.
Okay, just saying.
I think we're okay. Got that covered up there. All right. Inverses. All right. So now I want a times something is equal to 1. So this is related to this multiplicative identity. But now I'm asking, what do I have to put in here? A times a inverse. And in the scalar case, what is a inverse? What do I have to multiply it by?
1 over a.
Yeah, it's just 1 over a, right? I mean, you know, you already read this as an exponent. You see that inverse and you read it as an exponent, right? If it was a squared, you'd multiply a by itself. If it's a to the minus 1, that's 1 over a. It's a, anyway. And if it was a to the 0, it would be 1. So this is just 1 over a. And what about the inverse over here? And that's actually where we're going today. The rest of today will be like really understanding how to think about this. But you know that inverting a matrix, right? What do I multiply? We're still going to use the same notation, and write A inverse, and that's supposed to be equal to the identity. And how do we compute this, right? So this was easy to compute. You just take your scalar and you divide by, you take 1 over that, and you only have to be careful that A is not 0. We could write that here, A not equal to 0, because if A is 0, then this is infinite, and then that inverse is not really defined. Okay. That's because if you multiply something by 0, you can't get it back. You can't invert that process. Once you smash it to 0, it's gone. There's nothing left. It's just 0. 0 is always the same, no matter where you started, so you have no memory of where you were. Think of it that way. You take what you started with, whatever number it was, you smash it to 0, there's no going back. It's done. That's the end. It's kind of depressing. So you've got to stay away from 0, unless you really want it to be there. The same basic concept is going to be true here. It's going to be about multiplying things by 0. You can't invert things that get multiplied by 0, but everything else you can invert, and that's going to be the trick to understanding what this is and how to compute it. Okay, so that's basically what we're going to do today. All right, so I think we're all set up for what we want to do. Now there's one other thing, since we were talking about transposes. What happens if I told you that everything in this list, I'm writing it for matrices, but these could just as easily be vectors, because vectors are matrices. They're special matrices, right? They're 1 by n matrices. And scalars are matrices too. They're just 1 by 1 matrices, okay? So all of these things, think of them as a sort of nested family of things. There's the scalar, and then there's the vector. That's a bunch of scalars in a column. And then there's a matrix, which is a bunch of columns. It's a bunch of vectors, right? Or a bunch of rows, which are a bunch of vectors. Okay, so what if this, just like we had to go through this little thought process of what happens if I'm multiplying 2 vectors together. And we've talked a lot about this case where if we think of them as column vectors, we can write something like this. And if we do, let's see, if we transpose this one, then we can think about this as a correct description of a dot product when we think of these as matrices, right? Why? Because this thing is a column vector, but I transposed it, so now it's a row vector. And this thing is a column vector, and as long as they have the correct dimensionality, this dimension equals that dimension, this is a dot product. Right? That's the way we can express a dot product as a matrix multiply. Right? Everything is consistent. There's nothing new here. It's just notation, right? You transpose, you think by convention, I'm going to make the vectors column vectors. That's just a convention. We're going to usually think of vectors as column, unless specified other to be other, a vector is a column vector. If we tell you it's a row vector, then okay, it's a row vector, but usually, if we don't say it's a column, it's assumed to be a column. So when you write a dot product, you have to transpose the first one. And then it's correct to think about this as a dot product. It doesn't actually make sense to think about, if you're thinking matrix multiplication, two column vectors. You can't multiply two column vectors. You can multiply a row vector times a column vector if they have the same dimensionality. And that's a dot product. Now there is, of course, you can tell me, did Mike say this last time? This is what I couldn't remember. No? What happens if I flip this so that it's A times B transpose? So now this is the column, and this is the row. Think matrix multiplication. This is still a legitimate matrix multiply. Just like in the other direction it was an inner product. Now it's also a legitimate matrix multiply because this one has the same width as the height of that one. Its width is 1, and the height of this one is 1. That's okay. That's legit for matrix multiplication. So you can do it. This thing is not an inner product, though. What comes out of this when I multiply this by that? A matrix, because I'm doing dot products of all the rows of this, but those are just scalars, with all the columns of this, but those are just scalars. So I'm doing dot products that are just multiplications of scalars. And what's going to come out is every possible one of these elements multiplied by every possible one of these elements and put them in a table. So it's pretty easy to visualize. The way to think about it is, just draw it, let's draw it this way. I'm going to drop this a little bit. So here's the A, and here's the B transpose, right? And what comes out is a matrix. I'm drawing it like this, but you'll see why in a second. Because the width of this matrix, the number of columns, is the number of entries in this vector. And the height of this matrix is the number of entries in this vector. And each individual element, if I want to know what goes here, it's just the product of this guy and this guy. Okay? So this thing is an outer product, not an inner product. An inner product produces a scalar, takes two vectors and gives you a number. And that number tells you a lot about their geometry, remember? It's the product of their lengths times the cosine of the angle between them. But an outer product gives you something completely different. It gives you a matrix, not a number. And that matrix is filled with values that are the products of the pairwise entries of the vectors. Okay? You can think about this as, this will show up conceptually, this shows up in a lot of places. If we were thinking of these as not as, if these were vectors that were like 10 million long, and we were thinking of them as samples from some sort of continuous function, like a wave, like let's say a sound signal. This outer product is this it's kind of a separable product of two functions, right? So think about this as this is some function f of x, and this is some function f of y. The thing that comes out of this product, or g of y, is f of x times g of y, which is a new function, h of x comma y. Okay, so I'm doing something funny here. I just switched from thinking about vectors and matrices, which are sequences of numbers, to continuous functions. This is some function. And we did that already when we first introduced that spike plot, right? When I drew that spike plot, I said, well, imagine that these are just samples, like on a CD player, of some waveform. And this is some function of position, that's f, say f of x. So we can call, so we would, the words we would use here, we would say that h, function h, which is a function, a two-dimensional function on this, in this surface, is actually a separable function, because it's a product of a function of x and a function of y. So the idea of outer products kind of shows up in describing functions, and we're going to see this more and more, and when we get to probability, we're going to realize that this is, if these were probability distributions, we would actually have another name for this. We wouldn't say they were separable. We would say this is the joint distribution of two variables that are independent. So we're going to have another way to describe this. The same idea will show up, the same little bit of math, but we'll be using it in a different way. Okay, we'll get there. That's a bunch of weeks away. All right, so back to this outer product. This is just another thing that you do. It's just another special case of matrix multiplication, right? That's all it is. This is a product of two matrices where the matrices happen to be vectors, and now the first one is a column vector and the second one is a row vector. Notice that the dimensions of these two vectors do not have to be the same. If this one is really long and this one is really tiny, that's okay. You get a matrix that's not square. The matrix that comes out is it has a height of this and a width of that, but they don't have to be matched. They can be anything. So unlike the inner product where they've got to be the same, you cannot take an inner product of two vectors that are not the same length, because you're going to have to multiply pairwise all the elements and add them up. So everything has to match, but you can take an outer product with any two paired vectors you want. Okay, so we're done with all of that, and now we're going to solve this mystery. By the end of today, we're going to know exactly how you compute this, or whether you can compute this, because there's going to be cases where you cannot. And they're going to be strictly analogous to this. This is a case where you cannot compute the inverse, and then we're going to ask, well, what about if it's a matrix? Are there cases where you can? And we'll write those down. Okay, so let's do that. So Mike, last time, told you something that he gave you this Venn diagram. I don't know if everybody knows how to read a Venn diagram or how to think about a Venn diagram. I'm sure you do. That's also something you learned early on, even though you're sitting in class wondering, why are they telling us this? It's the problem with math. Return this on. It seems to have this is like just like everybody's living room. There's like several remotes up here. I don't know which one controls which device.
Oh, it's the one that's stuck on, sorry.
One that's stuck on
Here.
Like I said, somebody's TV in the next building just turned on. Sorry.
What's happening
Either that or I'm clicking through slides for somebody else's lecture. I can lay out it. We're on autopilot. Okay. So this was the Venn diagram. And,
Most of it is projected.
pardon?
The projectors.
The projector's
That's what I turned on. Thank you for debugging.
hit it twice.
Thanks. Okay.
It usually takes two.
It takes two. Oh, because you have to say you're sure. I really want you to shut up. Okay. It's lessons in conversation. Okay. So here's the point. Matrices. All linear systems, finite linear systems, can be described with a matrix. I mean, that's how we got to this. All of this nonsense about your rules about multiplying matrices and how you put the numbers together and whether it's rows and columns, all that stuff, it just emerges as rules from the very basic observation that if you have a system that's linear, it can be described by a matrix. And the operation of that system is matrix multiplication. Everything else comes from that. Everything we've done comes from that. Now, we're going to do something else. We're going to say, well, if you have a matrix, it can be any set of numbers. It's a box of numbers, right? rectangular box of numbers. Could be square, but generally rectangular. But it turns out that all matrices can be described in terms of a set of fundamental matrices. And the reason for doing this will become clear as we go forward. So the fundamental matrices are these two classes that are listed here in kind of, I don't know, some sort of sickly pink and some sort of very baby blue. Who chose these colors? I guess that was me. They look better on my screen. So the two families are the orthogonal matrices, and Mike walked you through last time how to think about those. I think the way that comes most naturally for thinking about these is that they're doing a change of coordinates. Okay? And that comes from the very first thing that we said about dot products and dot products onto unit vectors. So you remember this whole thing that if you take a dot product onto a unit vector, what you're doing is projecting your vector v, let's say. So here's v, and here's your unit vector. What you're doing is you're asking what piece of this lies in this direction, right? And we drew this diagram where you drop a perpendicular onto this direction, and you measure the length of this, and that's what the dot product gives you. It's a piece of geometry there, a little right triangle that tells you. What you're measuring is how far is this extending in this direction. And then you could, if you had another one, like if you do it for 2 on the board, right? You have a horizontal and vertical. You can actually ask about the projection onto both of them. And then if you wanted to take those two numbers, which are the projections onto those two things, and rebuild the original vector that you had, all you need to do is take the two unit vectors that are pointing in those orthogonal directions and multiply each unit vector by the coordinate in that space. So that description, which I just gave in words and which you saw written out, is really just multiplying by an orthogonal matrix and then multiplying by the same orthogonal matrix transposed. And you should, if you don't understand what I just said, you should think that through because you're going to have to work through these things. Let me just draw, make sure that at least you see what we're talking about in terms of rows and columns. Okay, so I'm going to erase this side of this little diagram that I was doing for scalar and matrix properties. And just say the following. So if I have a vector, let's call it v, and I have a rotation, an orthogonal matrix which I'll call R, I'm going to think about, the easiest thing is I'm going to think about the vectors that are in R as orthogonal, like perpendicular unit vectors. If I'm in 2 dimensions, there will be 2 of them. It's a square matrix. There's two unit vectors orthogonal to each other. And those are going to be the columns of R, because I like to think of column vectors as my convention. But I'm going to write R transpose here on purpose, because I want to think about the rows. Let's say those 2 rows. And what this is doing is taking a dot product of V onto those 2 rows. So what comes out of this are the coordinates of V. I have some vector V in my original coordinate system. Now I just measured the coordinates of V in this new coordinate system. I took a dot product onto these 2 guys, right? And how do I come back out? Well, it's easy. I just take the same 2 unit vectors and I take each unit vector and multiply it to get the length right by the coordinate in that coordinate system. How do I do that? Well, that's just another matrix multiply, and in fact, it's a matrix multiply with R. Okay, so Mike walked you through this in a fair amount of detail, but I just want to make sure that you see the general picture. Right? All this is dot product onto these coordinates that measures, these axes of the new coordinate system. That gives you the coordinates, right, in the new coordinate system. And then if I want to come back out, I just have to take those coordinates and multiply them by each of the axes. That's the 2 axes. I take the 2 numbers. This times this gives me a vector of coordinates. I take those new coordinates, multiply them by the 2 axes, and I come back out into my original space. So this thing is equal to V. And it's true for all V, so that means that R transpose equals the identity. And that means that for orthogonal matrices, the inverse question is easy. The way you get the inverse, the rule for getting the inverse for scalars was you have to take 1 over your scalar. For an orthogonal matrix, the rule for getting an inverse is you just transpose it. So R inverse equals R transpose. That's the rule. It's simple. There's nothing else to do. It's very easy. It's just transpose. Switch the columns and the rows. Okay. And it's always invertible. It's always invertible because what it's doing is, you should just think of it physically. It's taking your original vectors and rotating them. And nothing is getting thrown away. So to go back, you just rotate them back. Nothing is getting thrown away. In the scalar case, thrown away means multiply by 0. If you multiply by 0, you're doomed. It's gone. Okay, nothing can get multiplied by 0 here, because whatever vector you start with, if you're going to do this, it's a rotation. So you take it and you rotate it. It's not gone. It's just rotated. If I want to come back, I just rotate it back. Okay, so these are always invertible, and the inverse is just the transpose. It's really simple. You don't have to worry about whether it's invertible. And the way to think about, I'm describing, and we're shifting. I think this already happened. Mike started saying it, but I think I want to point it out explicitly. There's a subtle thing that happens that's very abstract, and so for some of you, it probably went by. Like, what was that? We're thinking about matrices being applied to individual vectors, and that's very concrete. So here's a vector, here's a matrix gets applied to it, it rotates. Okay? But if you think about it, the matrix as an entity can operate on any vector. So if I'm doing a two-dimensional case, which is what I wrote here on the board, any point on this board, if I draw some coordinates, axes here, this is my standard axes, this is going to be true for any vector. So any position on this board is going to count as a vector, and this matrix R is going to rotate that vector to the new coordinate system. So I can start, instead of thinking about individual vectors, I can start thinking about the entire space. I can take this whole board, and if I were strong enough and it were not properly attached to the wall, which I wouldn't be surprised if it was not, I would pick it up and I could rotate the damn thing, right? Notice, by the way, that I would have to rotate it around this coordinate x origin. The rotations we're talking about are always around the coordinate axes where they meet y.
Otherwise, it's not linear.
Otherwise, it's not linear. So, but I want something more specific.
Our 0 would go somewhere else.
Okay, right. So there's a concrete way to say it. If I start with the 0 vector, what happens when I multiply the 0? If b is the 0 vector and I multiply it by r, what do I get? All zeros. So the 0 vector has to get mapped to the 0 vector by one of these rotation matrices. That means this point is fixed. We call it a fixed point, actually. So this is a fixed point. And when I rotate, this is always going to stay right where it was. I have to rotate around this. I'm not allowed to rotate around some other position. If I want to rotate around another position, well, I can't do that with a matrix. What I have to do is take this vector, add some offset to it to move it. The 0 vector now becomes something else. I have to add a constant vector to it, and then I can rotate that. And that would be rotating around that other point. We'll see some more of that later, but just so you know, that's not quite a linear operation. It's a little bit more. It's not hard. It would be something like this. R transpose times V plus, let's call it A. So A is the offset that I'm trying to add. I'm going to add a vector, and then I rotate. And then I could maybe, when I'm all done, I could subtract off the A so that I put the 0 back where it was. Now I just rotate it around another point, not around the origin. I rotate it around A. Okay. So the point I wanted to make was that instead of thinking about operating on individual vectors, we can imagine operating on a whole space. The entire space is being rotated. That's the action of this matrix is to rotate the entire space. And that's how we want to think about it. We want to think about that geometry as being a sort of rigid rotation. Now the only subtlety is that it's not quite a rigid physical rotation. You can get yourself into trouble by thinking it always is. And I think Mike mentioned this to you last time. I'm going to use this same picture, but yeah. Maybe I'll just do this. An orthogonal matrix rotates, but it's also allowed to invert axes. So for an example, did Mike do this one? Mike, did you give an example with a -1?
I didn't write one down.
Okay.
Yes.
So here's a matrix. It's got one, it looks kind of like the identity matrix, but it's not the identity matrix because it has a -1 here, not a 1. Okay, this is an orthogonal matrix. How do I know? I can just check that the column vectors are unit vectors and they're orthogonal to each other. This column vector has length 1, right? 0 squared plus minus 1 squared equals 1. Done. But this one has length 1. 1 squared plus 0 squared is 1. The dot product of this and this is 0. Because this 0 hits this 1 and this 0 hits this -1, so I get nothing, right? So they're orthogonal and they are unit vectors. So this is an orthogonal matrix. What are the vectors that are in these columns? Well, one of them is the 1, 0 vector, which is the usual one, E. It's that one, right? That's the 1, 0 vector. And the other one is, 0, -1. So instead of being this axis, it's this axis. Okay, so it's a little bit weird. If you apply this orthogonal matrix, what you're doing is you're changing your coordinate system, and instead of representing the vectors on this board by a coordinate system where the first coordinate is how far you are horizontally and the second coordinate is how high you are, now the second coordinate is how low you are. It goes this way. It's the same information, it's just you flip the sign of the vertical coordinate. That is an orthogonal matrix. It is not a rotation. Why is it not a rotation? There's no way to rotate these two axes. Let's do it this way. So here's two axes. This is horizontal, this is vertical. My thumb is the horizontal. There's no way to rotate these two axes. Just rotating. So that the vertical one is now pointing down, and the horizontal one is still pointing this way. To do that, the only way for me to do that is I have to do this. And what did I just do? I cheated. I flipped my thumb in the third dimension, like in the z direction. Right now it's pointing toward me. I flipped it in the z direction, so I had to go into a higher dimensional space in order to flip this around and make the axes like this. But this is an illegal transformation. If you're only allowed to stay in 2 dimensions, it's not a rotation. And similarly, if I were doing a 3D thing, a 3D orthogonal transformation, and I had a box from Amazon, because all boxes are from Amazon, and I tried to describe what would happen to that box if I applied an orthogonal transformation to it, it might be just a rotation of the box. But it might be that I have to take 1 dimension of the box and smash it through itself and pull it out the other side, which is not physically possible. It's like everything inside the box has gone from a left-handed coordinate system to a right-handed coordinate system. The only way for me to go from a left-handed coordinate system to a right-handed coordinate system if I'm holding coordinates like this is to switch hands. Right? I can't make my left hand into my right hand. It's mirror symmetric, but I can't deform it into the shape of my other hand. If I try, it's not going to look right. I have to switch fingers. Right? So the only way to do it is a non-physical operation to smash, to invert axes. Inverting axes is allowable in an orthogonal transformation. It's not allowable in a rigid rotation. So everybody follow me? Okay. So when you think about orthogonal matrices, you should think about them loosely as rotating the space, but keep in mind they might also flip some axes. Okay? And they can flip any axes they want. You can flip one axis, flip another axis, flip all the axes, flip any subset. Okay. So that's it for these guys. It says here, performs a rotation of the vector space with possible axis inversion. That's what that means. All right? Then we have the diagonal ones, and those are really very different from the orthogonal ones, because there the constraint is not about unit vectors and dot products between columns, which is what defines these guys. Here the constraint is just that they have to be 0 off the diagonal. They don't have to be square, they just have to be 0 off the diagonal. That's the only constraint. So they have very few entries that matter. All that matters is what's on the diagonal. If I tell you you have a diagonal matrix, all that matters is what's on the diagonal. Everything else is automatically 0 by definition. And those act on vectors they do not rotate. They can't rotate. All they can do is take the individual coordinate axes and stretch or compress them by different amounts. Each diagonal entry tells you how much to stretch or compress the corresponding axis. And now's where you see the entry of this point that we saw in the scalar case. These things are invertible as long as they don't throw anything away, is the sort of short version of the statement. It's the same as this. Throw anything away means there's a zero on the diagonal. If you have a zero on the diagonal, then that entry in your input vector is going to be thrown away and you cannot recover it. It's gone. Same, just the scalar situation. You cannot invert that because it's been thrown away. If there are no zeros, and if the space you're going into is as big as the space you started with, then it's invertible. And it's invertible using this rule. You just take each of the axes that got squished or stretched and you undo the squishing or stretching. 1 over the stretch factor that you have for each of those axes, and that's the inverse. Right? Yeah.
Does the diagonal always start at position 1, 1, or can it start at 1, n?
Always starts at 1, 1. The way we're defining, so you'll see in linear algebra books, sometimes people have different ways of talking about diagonal matrices, but for our course, and I think probably the most common convention is to do what we're telling you, which is to always think of the very upper left-hand corner is the first potentially non-zero entry, and then you work your way down from there. If the matrix is short and fat, then you're going to hit the bottom before you get to the end. If it's tall and skinny, you'll hit the side before you get to the bottom. And if it's square, you will go all the way to the far opposite corner. Right? So it's just a question of whether it comes down here or whether it, right? There's different shapes. But it's only these entries that are allowed to be non-zero. Everything else, I'll put a big fat 0 here and here. Everything else must be 0. Okay? That's the rule. If that's true, then it's a diagonal matrix. And of course, the intersection between the diagonal and the orthogonal matrices is the identity matrix. That is both diagonal and orthogonal, but not just the identity matrix. It's the identity matrix of all permutations where you can put minus signs on those ones that are on the diagonal. Because, like the one that I just drew, that is an orthogonal matrix. It's also a diagonal matrix. Okay? So the intersection in this Venn diagram between these two classes is those guys. All right, now we get to say, well, why did we do all of this? We define these two classes of matrix, and I told you these are special. They're precisely defined. They have really nice properties, and they have very different properties. They kind of cover opposite sides of the spectrum. There's a little bit of an overlap, but in general, these guys you think of as kind of rigid transformations. They preserve vector lengths. If I start with a vector of length 10, and I apply this, I still have a vector of length 10, guaranteed. If I start with 2 vectors that have some angle between them of 30 degrees, and I apply this orthogonal matrix to both of them, they will guarantee they will have the same length and they will have the same angle between them. And that means their dot product will also be preserved, right? Their dot product is the product of their lengths times the cosine of their angle, the angle between them. So if I go and apply an orthogonal matrix, dot products are preserved, angles are preserved, lengths are preserved. It's kind of rigid in that sense, right? These guys rotate and they have the same relationship to each other. This is not true of these guys. In general, this does not preserve vector lengths. It can, like these guys do, because they are orthogonal and diagonal. But in general, these guys do not preserve vector length. They don't even have to preserve dimensionality. And they certainly don't preserve angles. So they really mess with the space. They can squish and stretch and throw things away. They don't preserve anything, or they're not guaranteed to preserve anything. Okay, so that's what's going to give us all the power, the difference in the properties between these two things. Yeah. Oh, you're going to make me stop now.
No, I'm just thinking that
Now's
might be
a
the
good
convenient
time.
place.
Okay. I hate stopping, but I'm going to give you 3.5, 4 minutes. Keep going. Because now we get to this is the punchline. This is the punchline of all of linear algebra. I think Mike mentioned to you last time. Usually, in a linear algebra course, you spend essentially the entire semester working toward a proof of the thing that is on the screen. Because it turns out it's actually kind of tricky to prove if you really want to be careful about it in the mathematical sense, rigorous, formal, and build it up and get to the point where everything is rock solid. It actually takes a whole semester. We are cheating. We're admitting we're cheating, so it's okay. We're cheating. We are going instead, our goal here is not really to turn you into mathematicians, but to give you things that you can use. And this is the most powerful tool in linear algebra. It allows you to solve essentially all problems. So this is, it's like the Swiss Army knife of the field, and it's really simple. It is a factorization. So it's a description that any matrix, so we already have any linear system can be described in terms of a matrix, and now we're going to say any matrix can be decomposed, written as a product of three matrices. Why the hell would you take one matrix and turn it into three matrices? That time sounds like you're making 3 times as much trouble, because the three matrices are of particular types. They're not arbitrary matrices. They are matrices described in terms of the things that we just had on the Venn diagram. Okay. So any matrix M can be rewritten as U S V transpose, where the U is an orthogonal matrix, the S is a diagonal matrix, and the V, which by convention is written transposed, and you'll see why, is another orthogonal matrix. The U and the V do not have to be the same orthogonal matrix, and in fact, they can't always be the same orthogonal matrix, because remember, this is true for any matrix that doesn't have to be a square matrix. So if M is a rectangular matrix, its input space is, let's say, smaller than its output space, then, of course, these two matrices U and V are not the same dimensionality. They're both square. And V has to operate on the input space of M, vectors that lie in the input space of M. So it has to take the lower dimensional thing. So it's a small square matrix, and U has to operate or hand back something in the output space of M. So it has to be in the larger dimensional space. So these are not even necessarily the same size, but they're both orthogonal. So the key thing about writing it this way is that we now have all the intuition and geometry that comes from those two different classes of matrix. The V transpose is a rotation of the space. So it takes the input space and it rotates it somehow. The S takes the rotated space and squishes it or stretches it in various directions along the axes. And then finally, the U takes those coordinates after they've been in the rotated coordinate system and after they've been squished or stretched. It takes those coordinates and spits them back out into the output space along a new set of axes that are the columns of the U matrix. So we're going to project onto the columns of the V matrix, because V transpose means we take dot products with the rows of V transpose, which are the columns of V. Right? So we're going to project onto, take inner products with the columns of V. Then we're going to multiply them by these scalars that are in the diagonal of S. And then we're going to spit them back out in the output space using U. It kind of looks like what we already said about inverting these things, right? So if I get rid of the S, or if S is the identity, so I can ignore it, it doesn't do anything. Then this is just an orthogonal matrix times another orthogonal matrix. Then they have to be the same size, of course, otherwise it makes sense. And you could imagine that these two orthogonal matrices, if they were the same orthogonal matrix, then this would be the identity. U times V transpose, if U is equal to V, then U times V transpose would be the identity, because the inverse of an orthogonal matrix is its transpose. So you see that that sort of transpose, that's sort of the case where the two vectors, these two orthogonal matrices are the same, kind of boils down to these special cases where it just is an inverse statement. But in general, that won't be true. And this is going to be something that we can do for any matrix. Okay? So again, the purpose of this, there's really 3 purposes for doing this. I said, like, why would you possibly write one matrix as 3? The first one is what I've been saying, which is that it gives you a sort of conceptual or geometric understanding of the action of a matrix. Any matrix can be thought of as acting by rotating the space, stretching axes, or compressing them, and then rotating again. Okay, so that's like a geometric interpretation of what's going on when you apply a matrix. And that means it's a geometric interpretation of what a linear system does, right? Because a matrix is a description of a linear system. Second thing, so you get geometric intuition. Second thing, it turns out that many, many problems, and we're about to go through a couple of weeks of least squares problems, every single one of those least squares problems can be solved using this. you can actually write down the same way you learned in high school to solve a quadratic expression, right? So you write down a quadratic formula, and you say, find the zeros. How do you do that? Negative b plus or minus the square root, you know, all of that. Divide by 2a, all of that, right? Remember, there's a formula, a closed form expression that tells you how you solve for the zeros. And it always works. You just plug in, and you know that that will give you the two values. It'll let you factorize, if you like, the quadratic expression into a product of two essentially linear functions, right? Two linear expressions. So this is kind of like that. By factorizing the matrix into these things, it turns out that that's going to allow us to solve, if you like, optimization problems. We're going to be able to solve regression problems. We're going to be able to look for places in a space of data that are interesting or that are not interesting. We're going to be able to separate things out. And all of that will come, and you'll be able to get all of those things in closed form. That is, you'll be able to write down an equation that tells you the answer by using this and by reasoning about this. So that's the second reason. So one is geometric intuition. Two, we actually can solve lots of problems, especially least squares problems. And the third thing is something that won't be apparent to you for a while, but it turns out that there are cases in the modern age of computation where computing this is faster than computing that. So why, so you kind of ask yourself, well, how could that possibly be? This is multiplied by 3 matrices, and in fact, the middle matrix has the same dimensionality as M, if that wasn't obvious to you, right? The V and the U are square matrices, so they preserve dimensionality. This one preserves the input dimensionality. This one is the same as the output dimensionality. The S that sits in the middle has to be the same shape and size as M. So if M has 100 columns and 50 rows, S will also have 100 columns and 50 rows. But of course, applying S is cheap. If I'm working in a computer and I'm writing code to implement the applying S, if I know that the matrix is diagonal, I don't have to multiply by all those zeros. It's diagonal. It's filled with zeros. It's mostly zeros. In that example I just gave you, it's 50 times 100, right? So 50 times 100 is 5,000. There are 5,000 entries in that box, and most of them are zero. How many non-zeros? 50. The diagonal's 50, right? It's the smaller of the two dimensions. It's a 50 by 100 matrix, but there's 50 diagonal entries. So in fact, to represent that matrix in a computer, I don't have to store 5,000 numbers. I only have to store 50 numbers, because I know the rest are zero. And when I go to do the matrix multiply, I don't have to multiply by 5,000 numbers. I have to multiply by just those 50. So that is a cheap operation multiplied by S. U and V may or may not be cheap. It depends what U and V are. If you're working in a situation where ahead of time you know what V, U, and V are, then maybe they can be pre-computed, or they can be you can operate even in hardware to transform things into the right space, like the V space. And then applying S is really easy, because it's just multiplying each element by a scalar. Right? Storing S is easy, and multiplying by S is easy. So it's cheaper for storage and computation. So the point, I'm just trying to give you a little illustration of that this actually can turn out to be faster and less expensive in terms of storage in a computer. Because matrices can get really big. If I'm operating on the contents of a CD, 44,000 samples times however many seconds you have of music, it's a huge, huge vector. And the matrix that's going to operate on that is a huge, huge, huge matrix. You don't want to store that in memory. You have to do that faster. And you're going to be able to do that often by taking advantage of explicit structures and properties of the matrix. And this is an example of explicit structures that are going to save you time and storage. Okay. So let's kind of go through. So I already said this. We're going to think of, because of what we know about orthogonal matrices, when we apply this to a vector, let's call it X for the input, vector X, the rows of V transpose are going to get, those are orthogonal vectors, and we're going to take dot products of those rows against X. Of course, the rows of V transpose are the columns of V. So what we're doing is we're projecting X onto each of these normalized unit vector axes, okay? So we're going to think of them, the word basis has appeared. We're going to think of these as like, columns of V are a set of coordinate axes, a basis for the input space. And we're converting the input space from its standard coordinates, it comes in X, Y, Z, we're going to convert it into these new coordinates using V. And then we're going to squeeze or stretch it, and after we squeeze or stretch it, we're going to run it through U, which provides a basis, a coordinate system for the output, right? It's on the other end. Okay, so think of V as preparing the input. Let me say this a little bit. Let me just add something before I say this. S it's going to turn out, because of what we know now about inverses, right? V is invertible because it's orthogonal. U is invertible because it's orthogonal. The only question in this chain of events about invertibility is going to come with S. S we're going to have to examine to understand if it's invertible. We have to examine both its shape, its two dimensions, and also whether the elements on the diagonal are non-zero. Because if any of those are zero, again, back to the scalar case, you just threw something away. So S is going to decide for us. S is where all the action is. We're going to learn a lot about what this matrix does by looking at S. And in fact, we don't have to look at all of S because it's mostly zeros. We just have to look at those diagonal entries. What are those doing? What do they look like? That's going to tell us a lot about what this matrix does, what M does. Okay? So think of it as V takes the input space and prepares it for S. And S does the dirty work, smashing things or stretching things out by some huge amount. It does the disfiguring, right? It distorts things, S. And then U puts them back out into the world, right? So you're going into some internal space where S can do its business behind, closed curtains, and then it comes back out through U into its output space, okay? So U and V are like preparing or translating, if you like, the signal or the input vector into this internal space where the stuff is happening, and then back out into the output space. All right. Oops. Okay. My animations are, there we go. S determines what gets through. What do I mean by that? I already said it, right? The things that get through, the things that are going to be invertible, are the things that are multiplied by numbers that are non-zero. It's pretty simple, just like in the scalar case. I multiply by some number, I can come back by multiplying by 1 over that number, unless that number that I multiply by is 0. Okay? It's the same rule that we're going to be thinking about when we think about S. Okay, so the picture you should have in your head, maybe something like this. Here's a little square that has think of these 4 points as 4 different vectors. I could draw from the origin, I could draw these, a line to each of these, think of them as 4 different vectors. And I want to describe, I told you what we want to think about is generally what a matrix does to a whole space, not just what it does to one input vector. Rather than try to draw the whole space, I'm just going to draw these 4 input vectors. I'm going to show all 4 of them together and say, what does the matrix do? So M as a whole is going to transform this to something else. I'm imagining a 2x2 matrix here, of course, because this is a 2-dimensional input space, and I'm going to go to a 2-dimensional output space. And what is the action of M? Well, the first thing M does, you write it using the SVD as U as V transpose. The first thing it does to its input is not to apply U, right? If I put a vector over here on the right side and I multiply M times X, my vector input, it's U times S times V transpose times X. So the first thing X is going to see is not U, but V transpose, right? This gets applied first. They're in backwards order. We've already talked about that. I'm just reminding you. So the first thing I do to this is I run through V transpose, and that just rotates. Really, rotate should be in quotations here, because remember, it's rotate with possible axis inversions, right? Right-handed versus left-hand coordinate systems. It might not be just a rotation. In this particular picture, it is a rotation. Literally, it was rotated by, I don't know, something less than 45 degrees by I. Maybe 30 degrees, right? This square got moved over here. Notice also that it is rotating around the center of the coordinate system, right? Which is why this thing is kind of doing that, right? The distances are all preserved, the vector length. So the distance from the origin to this cyan point is the same here as it is here. The distance to the red point is the same here as it is here. the green point, the blue point, all the distances are the same, all the angles are the same. The distance between any two vectors is the same, and the distance actually between the difference of these two vectors and the difference of these two vectors, which is 90 degrees because this is a square, that's the same. Everything is kind of rigid. Right? This square is still a square, but it's rotated. It's kind of a square if you tilt your head 30 degrees. Okay, now S operates, and in this particular picture, I think the way I did this is S is multiplying the horizontal coordinate by something like 2, so it's stretching it out. It's multiplying the vertical coordinate by a half. And you can kind of tell that by eye because this red point, which is here, ends up down. And this green point ends up further to the left. And this cyan point is further to the right. And so the horizontal coordinates look like they're about twice as big as what they were here. And the vertical coordinates look like they're about half of what they were here. So I'm guessing that this is multiply vertical by half, multiply the horizontal by 2. In other words, it's a diagonal matrix whose entries, just to make sure everybody's following, it's this diagonal matrix. Perfectly reasonable diagonal matrix. Different action on the two coordinates, right? One is being squeezed, one's being expanded. That's kind of interesting, actually. You can already see something a little bit. What's the area of this polygon? Well, the square. So let's just say it had unit area because I didn't show coordinate values here. So let's just say that square is a box that has area 1. It's a 1 by 1 square. What's the area of that thing?
One.
How come?
Product of 2 and pi.
So give me an intuition for why that would express the area.
So it's better to imagine a square that is
Aligned.
aligned
This one, for
and-
example.
Yeah.
Okay, so apply that matrix to this square. You reduce its height by 50%, but you expand its width by a factor of 2. And if you work for UPS, you know that that preserved the area. I guess they do it for volume. You know, when you go and take your UPS box, you have to give them the weight and you have to give them the 3 dimensions. And I always thought they just measured the volume, but actually they really do care about how different the 3 distances are. See, if you have a cube, that's a different difficulty to ship a cube than a really, really, really long box that has the same volume. Anyway, I don't know why I'm telling you this, because it's irrelevant. But try going to UPS and shipping a really, really long box that has, or try just putting into their online app, you can get pricing for sending things that have equal volume, equal weight. Their prices are not the same, it actually doesn't just depend on the volume. Okay, but this thing and this thing have the same volume. Because we're squeezing one axis and we're expanding the other axis, and they're kind of equal and opposite amounts, right? So think of it as like a fluid, and it's like incompressible, right? You squeeze this thing down by a factor of 2, and it stretches out this way, right? And you squeeze it this way, and it gets taller. You could do that, and you wouldn't be changing the volume. You're just kind of smooshing it in one direction and expanding it in the other direction by the same factor, or by the inverse of that factor. Okay, so this thing has the same area as that. And then the last step, of course, is another rotation. So I'm going to take this and rotate it one more time. In this case, I don't know what that is. That's not quite 90 degrees, but that's maybe, I don't know, 75 degrees, something like that. Okay? Okay, so we started with 4 points, 4 vectors. These are just examples, these 4 corners. They're 4 example vectors. What you can think about is the entire space would get rotated, or any point in space. These are just 4 examples to sort of illustrate geometrically what's happening. Those 4 things are getting rotated, stretched, and rotated again. They end up, they're all still here, they just have a different configuration. And this thing is invertible. Why?
Nothing went to 0.
Well, how do I invert it? Yeah, I mean, you can just kind of see it, right? What would I do to invert this? Well, I went through three transformations, right? First of all, each one of those transformations is invertible. That's actually the key here. We know that these 2 rotations are invertible because rotations are always invertible. Orthogonal matrices are always invertible. The inverse is the transpose. And geometrically, the inverse is just rotate back. You rotate this way, rotate the other way. And it's pretty straightforward to imagine that geometrically. You're just taking this thing and take this and tip it back where it was. Same thing here, it's a little bit harder to see, but this thing is rotated. If I want to go back, just rotate it back. And the only one that's a questionable one is going to be this one, the S. And in this particular case, what's drawn on the screen, nothing got lost. It's on the board there. I multiplied by 2, the horizontal axis. I multiplied the vertical axis by half. So how do I go back? Well, there's another matrix. If this is S, what's S inverse? Kind of looks like S. It's also diagonal. The inverse is a diagonal matrix. Inverse of a diagonal matrix is always, if there is an inverse, it's always another diagonal matrix. And it has on its diagonal just 1 over the elements of the original matrix. So this thing got stretched, I have to squeeze it back. This thing got squished, I have to stretch it back. And if I do that right, then I go back to where I was. Okay, so to invert this is really easy. Start from this end. You apply U, well, the inverse of U is U transpose. So to go backwards from here, I have to apply U transpose. Then I have to apply, well, it's that S inverse. Again, it's in general if it exists, but in this case it does, so that's fine. Now I'm back here, and now V transpose, V. Because I have to apply, this is an orthogonal matrix, I have to apply the transpose of this matrix, but this matrix is V transpose. So if I transpose it again to get the inverse, that's V. I'm back to V again, right? Transposing something twice just puts you back where you started. So this is V transpose, I transpose it to invert it, and that means I apply V. So, bang, bang, bang. So what we just said is that in this simple case, if I want to invert this, I multiply it by, first I multiply it by U transpose. I just want to write the math so that you can see that this actually makes perfect sense. I multiply by U transpose, then I multiply by S inverse. Again, I'm writing them in backwards order, right? Because I'm going to apply this first, then S inverse, and then V, not V transpose, V. And why does that invert that? Here, right? Here's M, and I'm trying to write M inverse. I expand M this way, and now I say, oh, the way I invert this is I think of this as laying down these sequence of transformations. Now I have to peel them off one by one, working backwards. So first I have to get rid of the U. I multiply by U transpose. Then I have to get rid of the S. Well, let's actually write this out. Let me get rid of the parentheses because associative rule, right? Remember, here it is, it's still here. Associative. AB times C is A times B, BC. Erase that, sorry. Associative rule, I can move the parentheses around if I have a stack of matrices that are multiplied by each other. So these parentheses don't matter. I can just get rid of them. This is just a big, long product of matrices, one after the other. So get rid of all the parentheses. They're all gone. And now notice that, oh, U transpose is next to U. Identity. Because U transpose U is the identity. Because U transpose is the inverse of U. Because I know that U is an orthogonal matrix. That would not be true if I didn't know that, but I do know that because this is the SVD. That's the whole point. Okay? Done. That one drops out. The identity means I don't have to write it because it doesn't do anything. Okay, so now I'm left with V. If I get rid of the I, I'm left with this. And I say, ooh, I've got S inverse next to S. If S inverse exists, then this thing is the identity again. It goes away, doesn't do anything. And now I have V times V transpose. Oh good, V is orthogonal also, so this thing is the identity. That thing is the identity. And that means that the whole thing is the identity. Okay? So M inverse times M is the identity. That's what we want out of an inverse. It's supposed to undo the action of M and put us back where we started, which is what the identity does. It doesn't do anything. It leaves you where you started. And we can express the inverse of M by doing the SVD and writing this. Okay? So a matrix is invertible if S is invertible. We don't have to worry about U and V. Those are automatic, right? So, okay. Let's do, and I'm going to come back at the end to sort of rectangular cases because that's a little more complicated to think about, but all the rules, everything we're talking about still applies. It's just a little bit more complicated to work through. Let's do a couple of other things first. So the first thing is, if I write this out and I think about what's happening to columns and rows, and I try to make some sense out of it, let me do it with some colored markers. So I have U S V transpose. So I'm going to think about, again, for V transpose, I want to think about the rows, because it's a transpose. I'm usually going to be thinking of the columns, but this is transpose, so I'm going to think about the rows. For U, I'm going to think about the columns. So let's do U over here. I guess I'll put 5 in here or something. Now let's stick to a square one, okay? Just because it'll be easier to draw the pictures and describe, and then we'll come back at the end. Okay, and then in the middle is S, and that has just these non-zero entries, 1, 2, 3, 4, and lots of zeros here and here, which I'm not going to write. I'm just going to put a big 0, but actually it's a whole upper triangle of zeros and a whole lower triangle of zeros. Everybody knows that, right? This big fat 0 means the rest of this matrix is filled with zeros. There are the potentially non-zero entries. Okay. What happens, how can I think about, if I do the matrix multiply, I want to think about the following. If I have an input vector, let's call it x, just write x. The reason that I'm writing this as V transpose is because I want to think about x as being like taking a dot product against unit vectors. These are unit vectors. There's 4 of them. So I'm taking a dot product of x with each of these unit vectors. I'm going to measure all these 4 coordinates. I want to think about what happens to the piece of x that hits the first unit vector. So I think of x as dot product with this, and out comes a number. That's the first entry. So this times x gives me a vector, right? And it's going to be a 4 vector. I don't know what size x is. It doesn't matter. It's going to be a 4 vector. So I'm going to get the first number in that 4 vector is going to be whatever I get if I take a dot product of this guy. I want it because I'm going to use green. This guy, the first one, and I get a number. Now what happens to that number next? Well, I multiply by s. And that number is only going to see this. Right? That number will be multiplied by this. In fact, you could see that if we multiplied s by V transpose, what's going to happen? I'm going to get this number, the first element in this diagonal, gets multiplied by that whole, is going to get, when I go through my matrix multiplication, this number is the only thing that's going to touch that row. And that entire row is going to get multiplied by this number, whatever it is. On the other end, so let's say I've gone through x, I've projected it onto this guy, I have a number, I rescale it by that. Now what happens to that number? Well, now I want to think about matrix multiplication the other way. So here I was thinking about the rows, thinking about dot products against the rows. But now, intentionally, I wrote this in terms of the columns because I want to think about the other interpretation, which is I'm going to take a weight in some of these columns. And what is the weight that gets applied to the first column? Well, it's whatever number I got when I took x times v and then multiplied it by this s. That number, it's a scalar, is going to multiply this column. And that's, so I can trace through this sequence of operations what actually happens. What's happening is I'm taking x, I'm projecting it onto this coordinate vector, and whatever, and I'm getting a number out, which is how far, what's the piece of x that lies in that direction. I'm going to take that number and I'm going to rescale it. And then I'm going to take that rescaled number, and that's a coordinate that I will use in the new axes. So that'll be, I'm going to multiply this unit vector by that number, and that'll be what I stick out in in the output space. I'm going to do that for each of these, actually. There's 4 of them. So what I get is a sum of x projected onto each one of these guys, multiplied by the associated s, and then stuck back out in the output space. I could write that piece of the operation, multiplied inner product by that vector. Let's write it down here. So I'm going to call this v1. It's a vector. And I'm going to put a transpose on it because it's a row vector. Then I'm going to write, I'll just write s1, which is a scalar. It's the first, I should write s11, because it's the 1, 1 entry of this matrix. But I'm just going to call it s1 because I only care about the diagonal, so I can just label these from 1 to 4. So that's s1. And then what do I have over here? I'm going to call this u1. And that's just a column vector. So this is the first vector out of u. This is the first vector out of v. First column vector out of v, but it's transposed, where you can say it's the first row out of v transpose. It's the same thing, right? It's just that since this guy's transposed, I'm pulling rows. So this is v1 transpose. This is u1. And this is s in the middle, which is just a scalar. And this is just a column vector times a scalar times a row vector. Let me, since this is a scalar, I can actually do plain old arithmetic for commutative law. So the s, I can pull over here. It's just a number, right? The number, the numbers commute, right? AB equals BA, if they're just numbers. And if it's a number times a vector or a number times a matrix, that also commutes. We can kind of move those back and forth. The problem is if I have a vector times a vector or a matrix times a matrix, then I have to think about the transposes, right? But here it's just a number, so I'm going to pull that out front. I have numbers sitting here. I'm going to put a dot for the number. And now I have this vector times this vector. What is that? Inner product? No. Outer product. This is an outer product. It's a column times a row. So this is an outer product of this, and then multiplied by this scale factor. And in fact, this whole matrix, it's m equals this, right, can be written as a sum of outer products, a weighted sum of outer products. Each outer product is one of these guys, outer product with one of these guys, and they're weighted by the s's. So this is just a way of fiddling with the math and rewriting this. And the way to think about it is, what you're doing is you're saying, project onto this vector, this unit vector, stick it back out, whatever you get, stick it back out in this space, multiplied by this unit vector. Oh, and by the way, rescale it by this s, while you're at it. Shrink it or expand it by this s. Okay. So that's just a way we can write that it's a sum of outer products. And let me, I think it's on the next slide. Yeah. Go ahead.
I have a dimensionality question.
Please.
So the number of columns in U, the number of rows in V should always equal the number of columns in X.
Yeah, so the way this is written is I drew lines in these two matrices. The number of lines have to all be matched up in that product. So however many lines I drew here, that's the number of rows of V transpose, has to be equal to the number of diagonal entries here.
Okay, so
And that
S,
has to be equal to the number of columns here.
okay, so S can't be arbitrarily large or small.
Wait.
What's on the board is the square matrix case.
Ah.
So that, and I lined everything up, okay? I told you we would come back to the diagonal case at the end. I don't want to mess with too much at once. This is in the square case, everything is kind of lined up and these things are all the same sizes. When we, okay? All right. I didn't tell you how big the input was, but in this particular case, because this is an orthogonal matrix, if it's got 4 rows, it has to have 4 columns. It can't be that it's got a different dimensionality. And that will always be true, of course. V is always squared. What is not always true is that U and V do not have to have the same dimensionality. Okay? And we'll come back to that. All right. Up at the top of the slide, is a restatement of what I just said on the board, which looks like this. M applied to X, we can think about applying the rows of V transpose, or the columns of V. These are dot products, V transpose times X. Then those numbers get multiplied by S, the appropriate S. Then those numbers get multiplied by the appropriate column of U. So this is just in math notation what I was just saying in words and trying to draw with that picture. Okay. And notice that out in front is a sum over K, because I have to sum this up over each entry. This is just one of them. If you rewrite this by essentially moving the U hat, this is a scalar. Okay, so I'm going to move the U hat over here, and then I'm going to move the parentheses around, because it's now U hat times V hat times X. I get this. I move the parentheses around, now it's U hat times V hat parenthesized, and the X is out here. And when I write it parenthesized like this is an outward product. Okay, so this is just a restatement of what I just told you on the board with slightly mathier notation. Okay. And it's a sum over K because you have to sum over each of these, right? Each of these rows, each of those columns. Okay, so now, this thing is called, I don't think I even said it. The fact that you're going to take M and rewrite it as U times S times V transpose, where those three matrices have the properties that I told you, that thing is called the singular value decomposition. It's just a way of factoring a matrix. That's how you should think of it. This is a factorization procedure. It can be computed. MATLAB has an internal function called SVD, singular value decomposition. SVD, just the initials, is what people usually use. And if you hand it a matrix, that function, it will hand you back these three matrices. You give it M, it gives you back U, S, and V transpose. In fact, if you call it without any return arguments, it just hands you back, so interestingly enough, it just hands you back the diagonal entries of S. Because those are the most important part. I told you that's like where all the action is. The decision about whether a matrix is invertible and how invertible it is, or whether it throws anything away, it's all made in those decisions, and those actions are all contained in S. And since S is mostly zeros, they're all contained in just the diagonal entries of S. And so by default, the SVD function in MATLAB just hands you back those diagonal entries. That's it. If you ask it to, it will hand you back the whole thing. It'll give you the U and the S and the V. But if you don't ask it to, it'll just hand you back the diagonal entries. Okay. Now we have to go on the board, or on the screen, is a non-square one. It's the same picture that I was just drawing on the board, but now the M is taller than it is wide. What does that mean? It means that the output space is larger dimensional or lower or higher, larger or smaller dimensional than the input space. Here's M. Am I going bigger or am I going smaller? Bigger. Bigger. Input space is this size. Can I give you the mnemonic? So if this is my matrix, I'm multiplying it by a vector. How do I think about that? I think about taking dot products with the rows, so I have to kind of tip it over. Let me get these the right size so I can take dot products. Here it is. Tip it over. Dot, 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 dot. Those are the dot products, okay? So here's the matrix. Here's the input vector. And I'm going to tip it and take dot products. Think of it as like a conveyor belt. And I used to do this with a prop, but I don't have it anymore. There's a pasta shop on Houston Street in Sullivan called Raffetto's. It's been there since 1906. It's run by a family. They own the building. They live there. The grandmother sadly died last year, actually. But they've had it for like 3 or 4 generations, I think 4. And you can meet them. They're lovely people. And they have, why am I telling you this? Why do I have a machine. The machine is not from 1906, I'm not sure, but maybe it's from the 1950s. It's kind of made out of cast iron, and it has a conveyor belt on it. And when you ask for your pasta, you want fresh pasta, you tell them how thick you want it to be, and they bring out a big sheet that they have with spinach or with pepper or with squid ink or plain egg or any kind you want, but they bring out a sheet and they load it up on the conveyor belt and they start this thing up and it starts running. Jum, 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 jum. The jum, jum, jum is a little chopping thing. Chop, 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 chop. And then they set the speed of the conveyor belt according to the thickness of pasta that you want, and they put the sheet down and it goes under the chopper and gets chopped to the right thickness depending on how fast it goes through. So you can get really wide noodles, really narrow noodles. By the way, I'm telling you all of this as an advertisement for Buffettos because it's an amazing place and you should definitely go. It's like pasta is really great. But the other reason I'm telling you is, here's your sheet of pasta. And now you're going to put it on the conveyor belt. And you're going to go chop, 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 chop. So each of these little chops is a dot product. Dot, 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 dot. Okay, so tip, chop, 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 chop. And then you boil it for about 3 minutes. Highly recommended. Okay. So, that said, the rows of this thing are going to have to take, I'm going to take dot products of these guys with the input vector, so this better be the size of the input vector. The width of this is the size of the input vector, so what's the size of the output vector? It's the height. The height is bigger than the width, so the output dimensionality is bigger. This thing is taking an input space and splatting it out into a bigger space. If it was the other way around, if this was a short fat matrix, it would be taking a big input space and squeezing it down into a smaller output space. Okay? That matters a lot. We'll see it now. Okay? So here's this case where we're going into a bigger space. How does it actually work? Well, questions?
In practice, do you ever take your data to a higher dimension?
Absolutely. How do I describe why you would take your data to a higher dimension?
Well, like LGM to V1.
A vision example is a mystery for the field. The number of wires coming out of the back of your eye is about 1 million. But the number of cells you have in V1 is like 100 million. So if we think of those as doing something linear, well, why did you go to this much higher dimensional space? That seems silly. It turns out that many operations are easier to describe if you actually lift yourself into a higher dimensional space. And this has become a core principle and trick in machine learning. And they actually call it the kernel trick. Of lifting things into a higher dimensional space and operating on them there and then smashing them back down. So I don't have time to give you any detailed example of that, but we will see some things like that as we go through the course. Okay? We'll see simple examples of that. Okay. So what's going to happen here, we just use the SVD. It's the same SVD. The only difference between what's on the screen and what was on the board is now, of course, the U and the V are not the same size because the input and the output space are not the same size. The V is a little, let's say, 3 by 3, and the U is a, whatever that is, 7 by 7. Okay? Because it has to be square, so it has what's drawn as 7 columns, so this is a 7 by 7. That thing's got to be 3 by 3. This thing I'm showing the rows, that thing I'm showing the columns, again, because this one is transposed, so I'm concentrating on the columns of V, which are the rows of V transpose. And also because I want to think about what happens as I go through this operation. So it's the same story as what I already told you. I'm taking each of these things, I'm projecting onto them, I'm rescaling by the appropriate S, and then I'm spitting it back out in the output space. Now the only thing that's different is that I only have 3 of these, and these things are going to hit these 3 things, and these are the diagonal entries. There's nothing else in here that can be non-zero. When I have a diagonal matrix that's not square, it means the diagonal gets kind of cut off. It hits the wall, or it hits the bottom, and it doesn't go to the corner. That's okay. The rule is the same. A diagonal matrix is only allowed to have non-zero entries here. Everything else has to be 0. That includes all of this stuff. This thing has to be the same size as M, so here it is. It's a tall box. This is all zeros. And everything in here is zeros. There's 3 zeros here. 1, 2, 3. And there's 3 zeros up here. 1, 2, 3. And then there's a pile of zeros down here. How many? Well, there's got to be 4 more rows times 3 columns. So there's got to be 12 more zeros down here. Right? All zeros down here. Zeros here. Zeros here. These are the non-zeros. Okay. So what's this doing? That's the new part, right? On the board, I didn't have that. We just had these 4 guys, and that was it. 4 here, 4 there, we're done. Now all of a sudden, there's this extra stuff. What's that doing? Well, it's kind of weird, but if you think about it, like this column is going to see whatever comes out of that S1 entry, and that S1 entry is going to see whatever comes out of the inner product with this first row. The second column is going to see what came from this, that came from this. The third will see what came from this, that came from this. And what about the rest of them, the other 4? They got nothing. They're going to see 0 guaranteed. There's nothing they can see other than 0 because this was all zeros. There was nothing in the input that is going to have any effect at all. No matter what you put over here, nothing that you put over here can have any possible effect on these, what comes out of these 4 vectors. It's guaranteed to be 0. So it's kind of weird, but what that means is that when you do this, you're going to come out in this coordinate system defined by u. And this axis will have some stuff. It'll have a coordinate. This axis will have some stuff. It'll have a coordinate. This axis will have a coordinate, some value. And these are going to be like dead axes. They're sitting there. They're actually there, but their coordinate value is 0. So, you know, if we were doing this from 2 to 3 dimensions instead of 4 to 7, what you would say is, I'm going to rotate, I have 3-dimensional space. Here's my output space, right? Here's my 3 vectors. They don't have to be x, y, and z. They're pointing in whatever direction they point in. What I'm telling you is that I start with 2, and I'm going to end up with whatever comes in getting mushed around and smashed onto 2 of these coordinate axes in the output. But in the third one, it'll be 0. So let's say the third one is my thumb, and the other 2 are like this. That means that what comes out will lie in a plane defined by the 2 that are being used. And the third one, which is perpendicular to the plane, is not used. It's set to 0. So I'm going to start with some stuff in 2 dimensions, let's say on that board, and I'm going to end up with something that's on a plane. It starts on a plane, it's going to end on a plane, but the new plane will not be on this board. It'll be, in general, it'll be kind of angled out into the space somehow. And there will be a third coordinate, but it won't be used. Okay, so that's how to think about the action of this matrix. If I flip it around, let's do the other one while we're at it. Let me just change what's on the board. And now I want to do the short, fat one, right? Tall, skinny, short, fat. So now S looks like this, and V is big. Sorry. Let's make V, I don't know, V transpose. We'll just put 3 here, and now we'll put 2 here. These are the non-zero entries, right? And now I'll put a little 2 by 2 here. Okay, so this is an example of one that does the opposite. It is starting in a large dimensional space and bringing us down. And here, because this is diagonal and it's 2 by 3, these are the potentially non-zero elements. And this is 0, this is 0. This is, I hope you can see those are filled in. And then I have 2 zeros over here, so I'm going to draw a dashed line like that, just like the one that's on the screen. There's a dashed line that says everything below here is zeros. In this case, everything to the right of here is zeros, right? Because now it's too wide. It's not square, it's wider than it is tall. And so these are zeros. In the case that I have drawn here, this is just 1 column of zeros, but if the input dimension was 10 dimensions, then there would be 8 columns of zeros, right? It's however many I need to match up all my dimensionality, right? Okay, so what does this thing do? Well, this guy, I project onto this guy and multiply by that, and then I come out in this direction. This one, I project onto this, I multiply by this, and I come out in this direction, right? These are the first one, the second one. What about the third one? what happens to that? That gets multiplied by 0. It's thrown away. So this automatically is not invertible. And in fact, anytime you have a matrix that takes a high dimensional space and brings you down in dimensionality, if you look at the SVD, you know immediately this can't be invertible, because at the very least, the minimal condition is that all the ones that are here that are associated, let's put a dash line here too, all the ones that are associated with these 0 entries of dimensionality that are lost, these are going to get thrown away. Remember the way this works, we have a 3-dimensional coordinate system defined by these 3 vectors, right? I'm going to project my input onto those 3 vectors. The third one, the one that goes in the direction of my thumb, that's going to get thrown away. Again, whatever comes in the input, if its component that lies in that direction is gone. This is gone. Cannot be recovered. Multiplied by 0. You can keep something that represents the other 2, and the way you would, how would you get back the other 2? This one is gone, but you can get back the other 2. How do you do it? Well, you multiply by U transpose. That undoes this operation. You invert each of these, assuming they're not 0. Same rule. If either of these is 0, then you have trouble. But if these are non-zero, you just take 1 over each of those entries, and then you come back out through these. You invert this. This is this little, like a rotation of just these 2 axes. So you can invert the part of this matrix that corresponds to these 2 entries. You can get that piece back. So all is not lost. Unlike the scalar case where if you multiply by 0, you're done. That's it. There's nothing else to say. It's gone. Here, there's actually a diversity of possibilities because we're going to start with, however, in this case, 3 dimensions. You're guaranteed, if you're going to go down to 2 dimensions, that you're going to lose something. 1 dimension gets lost. It's this guy. If this diagonal matrix had another 0, like a 0 here, uh-oh, now we lost something else. Now we lost this guy too. And if it had 0 here, that would be a really stupid matrix because that is the 0 matrix, and when you multiply all this together, it is the 0 matrix, but you still might be unlucky in that way. So if you have all zeros, then obviously everything is lost. So the amount of stuff that we lose is going to depend on what shows up in these entries. You have to examine them one by one. If they're non-zero, then you didn't lose that axis. And if they're 0, in this case, the last one has to be thrown away. And the decisions and the judgments about whether something is invertible come down to sort of understanding what's on those diagonal entries, and also what's the shape. Okay. All right. Let's see. I have, I think, a few more slides just to elaborate what I just said. So this is what we just said. So if these things are non-zero in this picture, then the piece that's you can invert easily is those 3 pieces, and everything is fine. And in the short and fat case that I drew, if those 2 are non-zero, then then you can invert the piece that comes through those 2. You cannot get back the 3rd one because it's already thrown away. Of course, even in this tall, skinny case, you're not guaranteed that you can invert these. And in fact, if that's a 0, this one, these 2, let's say, are non-zero, now I have to move the line up. All of these are 0. And now this thing gets thrown away. So this is, in the input space, these 2 vectors are orthogonal vectors that represent the stuff that is not being thrown away. You're going to kind of preserve it, or at least you can undo it. You might be squishing it around a little bit. You might be multiplying this by 2 and this by 1/2. Okay, but it's still there, and you can get it back. This thing is gone. This part is not invertible. And you can track that all the way through, and you can talk, there's names that we give for the part of the input space that is getting thrown away. That thing is called the null space. So the input space in this picture is a 3-dimensional space because there's 3 rows here. These are 3 orthogonal unit vectors. They're pointing in orthogonal directions, axes. Okay? These are a basis. They provide a basis for the whole input space. They provide coordinate system, right, for the whole input space. But now we can read off from the SVD that some of them are representing the stuff that's getting thrown away. Those give us a basis or a coordinate system for what's called the null space. That's the part of the input space that is getting tossed. It's getting set to 0. In this particular picture, this one axis describes the null space. Anything in that direction is going to get thrown away, and you will not get it back. So that's the null space is defined by that vector. And in the output, there's another thing that we can talk about, which is in that entire output space, in this case it's 7 dimensions, there's a big 7-dimensional space, you can ask the question, well, what things in the output space can I actually get to? Can I get to all of it? Can I get to some part of it? Is there like a piece of it that I can achieve? If I pick the input right, can I get to that point in the output space? The answer to that question can also be read off from the SVD. And the answer is, it's kind of clear that the only things that are going to get through are things that go through these two singular values, because this one is 0. And those two, whatever values get through, are going to get stuck into the output space along these two axes. So in this picture where there's 7 output axes, only 2 of them are going to be like active. Anything that comes out has to be a weighted sum of those 2 output axes, and you can't have anything else in the output. That means that the output lies in a plane defined by those 2 axes, these 2 axes. The output has to lie in that plane. It can't get off of that plane. To get off of that plane, you would have to add something off of that plane, like another vector that was orthogonal to these 2. Well, here's a whole set of vectors that are orthogonal to these 2. These are all orthogonal vectors, but you're not allowed to use any of those. Why not? Because those things are only going to see zeros. Anything coming through this matrix, by the time it gets here, these guys are 0. They're not used. Only these 2 can be used, and therefore the output space is, you can't cover the whole output space, all 7 dimensions. You can only cover 2 dimensions of that output space. We call the part that you can reach, the part that you can cover, the range space of the matrix. So this is the null space. That's the set of things that get thrown away in the input space. And there's the range space. That's the part of the output space that we can get to. And a basis, or a coordinate system for the range space is these 2 guys. And a coordinate system for the null space is this guy. Notice they're kind of like on opposite sides of the fence, the dashed line. Right? These are the ones that are below the dashed line, or if you were flipping this and making it V instead of V transpose, they would be to the right of the dashed line. These guys are the ones to the left of the dashed line. Right? These are the ones we're keeping and we can reach. These are the ones that are getting thrown away. They're hitting zeros. Okay. So this is the kind of thing, I know we're out of time, just this is the last slide. And it's the same statement, I've just moved it. I moved the dashed line up 1. Okay, so what if that's 0? Okay, well now, there's only one thing that's getting through. The output lies along a line. And that line is defined by this vector. Everything that comes out of this matrix has to lie along that line. It cannot get off of that line because it has no way to get off of that line, because it will be a rescaled version of this vector. And all rescaled versions of this vector lie on this line. So these are thrown away. This is preserved, or you can land anywhere along here. And on the input space now, only this thing is usable, and this stuff gets thrown away. So you have a 3-dimensional coordinate system. What you're saying is only the first axis is actually useful. The rest of it is going to get thrown away. This matrix is going to toss it. And whatever it keeps, the thing along that first axis is what's going to come out this way. All right. So this is like a little bit of working through and thinking about how we're going to use the SVD. We're going to think about spaces that are getting thrown away, spaces that we can get to, and we're going to think about computing inverses. How do we go back? How would you find, if I tell you that I want a point on this line, how do I get to it? Well, I have to kind of work backwards. In order to get to it, I have to rescale this vector by the appropriate amount to get to that point. That means the scale factor has to come out of this, so it has to be S1 times something. So if I divide by S1, I can figure out what value I'm supposed to have after I do this dot product. So I can kind of work my way through or backward figuring out what each of these computations are because each one of them is pretty simple. You know, these are unit vectors that are orthogonal. These are just scalars, and these are again unit vectors that are orthogonal. Okay, so Thursday, we're going to go through a lengthy example, one of the most beautiful examples I know. It's going to be a science story. So we'll take a little break from math, but we're going to put math into it and show you how to interpret the science story using the math that we just went through.
And finally, Friday this week is not a lab, it's a lecture. And it's a lecture that starts not at 9:30, because I'll be just getting off a tennis court, but at 10. And I will put that on Piazza, because I don't know if anybody can hear.